So we have an exam on Monday,
What?
right?
Yeah.
I heard a what back there?
You heard it right here.
Oh,
I was just kidding.
you're kidding. Okay. And the key to doing well in the exam is to practice. Don't practice the night before. You should have already been practicing. And practice means looking at the sample exam questions and even coming up with your own questions and maybe running these as code to see what happens. But you have to practice being like in the exam where you don't have a computer and you think it through. What does this code do? All right, so that's really very important. You need to practice this. So we may spend a little time talking about some of those problems, but let's finish looking at this lab 3. I think that's due on Friday, right? Is that right? 24. What is today? 22. Factoring numbers. How many people got this? 2, 3, 4, 5-ish, 6? Yeah, that's good. So let's do this one. Write a console program that asks the user to enter a positive integer greater than 1. The program computes the prime factors of the number and prints them. For example, if the user enters 100, the program displays 2255. 2 times 2 is 4, 5 times 5 is 25, 4 times 25, that's 100. So those are the prime factors of 100. Develop 8 test cases and verify that your program runs correctly for them. The test cases should contain some prime numbers as well as non-prime numbers. Include tests for edge cases, such as the numbers 2, which is the first prime, 4, the first non-prime. Develop test cases that try to break your program so that you are sure your code is correct. Include the description of the test cases in a multi-line comment near the top of the source code. All right, let's do this. That's good. So let's copy the solution to the first exercise. So we have a starting point. I picked that because we have 8 test cases in here.
That one's useful.
Huh?
That
Yeah.
one is useful.
Oh, this is useful, yeah. All right, let's look at the test cases first. It's always good to look at the test first. There's a strategy in programming or in software development called the test first strategy. So develop your test first. So the prime factors of 2 is simply 2. The prime factors of 3 is 3. The prime factors of 4 is 2 and 2. And 8 would be 2, 2, 2. And 9 is 3 and 3. 27, 3, 3, 3. 42 is 2. That's 21. So 3, 7. And 47 is just 47. Is that how we do it? And then I want to throw in 100 because that's in the problem description. So we don't have a lot of prime numbers in here, but we have this one. Do we want to display 47 or 1? Did I say anything about that? What are the prime factors of 47? Because 1 goes into all of these, right?
Yeah.
So it's 47. I think that's how we do it. All right. So enter an integer greater than 1. So we just have our test cases lined up and some input code here. Let's check to see if that's working. So 4, that's working. All right. So you can imagine the result could be pretty long, right? We can construct a number that gives us any arbitrary number of prime factors. So what's the construct that comes to mind there? The loop. Yeah, it's got to be a loop. So I'm gonna rough it out. You know, I don't have an answer in my head right now. I just see that and I think this is a loop. We got to do a loop here. We're gonna have to repeat something over and over again. And that's as far as my thinking goes right now. It's not like I see any beyond that. Of course, I've done this before. All right, so I know that I can take it easy at this point here. Okay, so, and I just made an infinite loop, just as a starting point. And I'm just going to rough it out here. Just going to think about it. So we've got a number, n. So n is the number that's come in. And what we need to do is find numbers that divide in and prime numbers. Now, I already know the trick to this program. So I used to do this in the long, difficult way, but now I know it's actually a pretty short program. And I'll show you the short way rather than the long way. So what we want to do is start trying prime numbers. We'll start trying 2. And if 2 goes into n, then we'll take a 2 out of n. Like, let's suppose we enter in 8 for n. And we'll start the loop with some divisor, call it k. So have some divisor k. And what we're going to do is take, n mod k and compare it to 0. So if k divides evenly into n, that's what we're looking for. So if we take n divided by k, like 8 divided by 2, and there's no remainder, that means 2 evenly divides 8. So this is the case where k is good, right? So if k is prime, we want to print k. So if n mod k is 0, that means if k divides into n, then we're going to print k. And I'll put it like this. I'll put a space there in case we're going to print again. So, but we only want to do this if k is prime. So we don't want to, if we have an 8 and k is 4, and 4 divides into 8, we don't want to print 4 because 4 is not a prime factor. 4 is 2 times 2. So for 8, we want to print 2, 2, 2. But if you look at these lists up here, you'll see that before we hit a 4, in all of these cases, this case, 4 goes into 4, 4 goes into 8, and 4 goes into 100. But in all of these cases, if we start with 2, we're going to take out enough 2's first to pull the 4 out, so that when we hit 4, if we're going up, if we're starting at 2 and we go to 3 and then 4, when we hit 4, we've already taken out 2 2's. And so we can just say, well, this expression will never be true for 4 or for any non-prime number, because the primes preceding it, we've already tried all the primes lower than it. See, if we start at 2 and we increment k in the loop, see how that works? Because we have to exit here. We're going to decide, while k, well, so see, so we got to have some sort of condition here. What is it? How do we finish this loop? I'm trying to show the individual pieces of my thinking process.
Within the loop, after we see out k, should we assign n to be n divided by k?
Yeah, exactly. Very good. That's the next step. That's right. And so we're going to print the k, and we're going to say, well, it's we got to take n, and we're going to remove k from n right there. So now, if n is 8, We're going to divide 8 by 2. That turns to 4. So now n becomes 4. Oh, but look at this. We don't want to increment to 3 because we have 2 more 2's in the case that n starts at 8. So we better put an else clause there. So we want to just continue the loop with the same k. If k divides into n, let's take it out of n, but let's not increment k yet because we may be able to take out several k's. The only time we're going to increment k is if we've exhausted all the possible divisions by k and reduced n accordingly and printed k multiple times. So you see n starts at 8 in the case that we're considering. That's this case right there. N starts at 8. The loop k starts at 2. This index k, or the number k. And then we take a 2 out, and n in this expression here, n becomes 4. We take another 2 out, n becomes 2. We take another 2 out, n becomes 1. N becomes when n hits 1, we're done, right? So there's the loop condition. While n is not equal to 1. So when n hits 1, we're done. And look at the case of 47. Does that work? Because we never find a k. 2 doesn't divide, 3 doesn't divide, because 47 is prime. So k is going to hit 47. And then we're going to go 47 mod 47. That will be 0. 47 divided by 47 is 1. It gives a remainder of 0. And then we take n, which is 47, divide by 47. It becomes 1. Now n becomes 1. And now the loop condition is false. So it works for that big prime number 47. So I'm just checking it mentally. Is there anything else we need to do? Well, I can think of a trivial thing to do. Let's just, I don't want the list of numbers to merge with the prompt, so I'm going to print an end line after we've done the loop. See, I put the cursor here to highlight up there, you see? So to show that this is a block right there. So that's a statement, that's one statement. When that statement finishes, we do the next statement, which is just to print a new line. So we don't, the string that we print doesn't, the prompt doesn't show up in our output string. All right, let's see it. Let's see if it works. And I'll do 47. That worked. What about 8? What about 27? That worked. I think they're all going to work. 2. That worked. These are test cases, right? What else? 100. 142. Let's try 42. And let's try, and that's right. And let's try 100. 2255. There we go. Did you think it was going to be that simple? Yeah.
I was having an issue at home using Visual Studio where it would compile the code and then immediately close.
Close the window, right?
Yeah.
This way, if you're using Visual Studio at home, when you execute the program inside the Visual Studio, you run in what's called debug mode. It pops open a console window for you temporarily, but when the program terminates, it closes the console window. So what you need to do there is you have to pause the program. And one way to do that is to simply call get on the standard input stream. And then the program will halt, waiting for the user to press enter. However, this won't work in this case because an enter character is in the input stream because the user entered in this n value. And the number, say 8, we entered it, when the user types in 8, return, that this statement right here returns. And the 8 gets pulled out of the input stream and put into n. But the Enter key, the character turn, is still in the input stream. So this will execute right away. So actually what we need to do is put 2 of them there. I don't know if anyone followed that. The second time I covered that. So if you're in Visual Studio, this is the trick. The other way to do it is you set a breakpoint, you know, at the end of your code. There's a bar, there's a section to the left-hand side of your editing window, and you can just click your mouse there, and you'll see a circle come there, and that's called a breakpoint. So your code will execute and stop at the breakpoint. So that's the other way to do it. Okay.
Made it very interesting to debug when you only have half a second to look at it.
Yeah, I had to look at it pretty fast. Maybe you take a video of it and then play it back. There's a third approach. You can go out to the file system and find the exe file in the solution folder. There's a debug. In your solution folder, there's going to be a debug folder. In there, there's an exe file. And you just run that at the terminal window. You have to open up the terminal window. You can run it directly. So there's 3 solutions for it. It takes a while to get used to Visual Studio, but the payoff is enormous. I mean, you can code much, much faster than doing VI, right? I do not recommend using VI. And see, these are baby programs for me. So VI is more convenient. I don't want to launch Xcode or, you know, because I'm on a Mac, so I would run Xcode. Or if I had Windows, I don't want to launch Visual Studio with all the project folder and the solution folder. I don't need all of it because these are just tiny programs. So it's cleaner for me just to use VI. But if I'm doing a real project, I'm not going to use VI. Well, unless it's small.
No one uses NetBeans anymore?
Well, NetBeans is all right, but Eclipse, I use Eclipse instead of NetBeans. It's the same thing. But that's they don't use that for C++ development very much. I don't know if NetBeans can compile C++, but Eclipse can. And then there's others, like Code Blocks. It's an open source IDE. It might be easier to set up and use. Some people like Code Blocks. It's free, open source development environment that runs in Windows. Also, it runs in Linux. I don't know if it runs in Mac. Yeah, it must run in Mac. Does it run in Mac? Code Blocks? I don't know. But Xcode is free. And if you want to be a professional developer, it's good to learn Visual Studio and Xcode, those 2. Because you can't learn Xcode if you don't have a Mac. But you can't learn Visual Studio if you don't have a Windows machine. So if you learn one IDE, one integrated development environment, then it's easier to learn the other one. And these things are very complicated. So they make coding fast and simple and easy. But you have to understand what's going on, and there's a lot of settings in there. When you create a project, you can link projects together, you can generate libraries, statically linked, dynamically linked, and it's all compiler settings, you know, 64-bit targets, 32-bit. There's just a ton of things to look at, you know, library linkages. There's so much complexity there. So once you start going down that road, you have a lot of learning to do. You're not going to get it right away. But that's what they use in practice, those kind of IDEs in general. All right, so that's this one. Any other, nothing else on this, right? This is the solution. You see it right there. Is this what you came up with?
No.
Did you check for primeness?
Yeah, I did.
See, what I used to do, I used to like get a K and say, well, I don't want to print K if it's prime, so let me check to see if K is prime. If K is prime, I won't print it. As I explained, that's not unnecessary.
Primeness came at the end for me. I had to de-increment it.
Oh, you de-increment it.
I had it all in a
Yeah.
for loop, and then it would normally increment. But if it did divide successfully, I de-incremented it back so it would recheck
Oh, I
it
see.
again.
Well, that's pretty close to the same thing.
Yeah, it's very similar.
Very,
It's not
very similar. You just did that instead of this.
the else statement. Yeah.
All right, so let's do generating random colors. Write a program that generates a different list of 100 random RGB color values using hexadecimal notation. the program should write something like the following into cout. So there's, that's a color value in hexadecimal notation, right? So for those who don't know this, this is 32 is a hexadecimal number. It's 3/16 plus 2. That's what it equals, right? So, in decimal, right? These are the ones, right? And these are the tens. And these are the hundreds. So that's 100. That's what 100 is. On here, this is a hexadecimal value right here, right there. These two, you can think of that. There's 3/16, so the second slot there is not tens, it's 16. So there's 3/16 and 2 ones. And this is 4/16, and how many ones? 10 ones. Because we ran out of old-fashioned digits, so we got to use A, B, C, D, E, and F. Right, F is 15. So this would be 15 16s, and 3 ones. So this is how color values are expressed, because this is how it's stored in memory. This is a byte right here. That's 1 byte, and you use 1 byte to store 1 color component, RGB. So this would be B, blue. Then this is green. There's 1 byte value to represent green, and a 1 byte value to represent red. And usually there's another byte in front there, because 3 bytes are a little odd, right? So it's normally 4 bytes. That's called a word. 3 is an odd number, so it doesn't work well, actually. Well, it's good to have another color value there as well. Do you know what that is? What's that called? They call it a channel. These are called channels, color channels.
Say that one more time.
There's another color component, RGB and something else.
CYMK.
No, RGBA. So alpha. Sometimes alpha comes first, sometimes alpha comes last. So you have to know when you're working at this level with color values directly, you have to know the sequence. That's CMY and that stuff there. There's other ways of representing colors. There's HSV, I think is another one. But this is the RGB way to do it. This is what you see in like web pages. So when you work with web pages, you use these values to specify colors. So we want 100 of these, and they should be random, fully random. So to solve this problem, you need to generate strings. But before I do that, let me get the shell of the program ready first. So we got to print 100 random color values. So that means we want a loop that runs 100 times. This is the standard loop that runs 100 times. This is how you would normally see it in code. There's other ways to express it, but this is the most common. And in here we print a random color string. That's it. That's what the program does right there. Let's simulate that. Let's suppose we have a random color string. I'll call it color. And maybe it'll be this one here. So we compute that thing, and then we print it. Followed by a new line. So I'm just stubbing this out. It's called stubbing. It's a partial solution. Just trying to rough it out from the beginning. And when you're doing this, look, I'm not just going to keep working. I'm going to test it right now. See? Test it right now. So what this is called an incremental development technique, and this is how it's done normally, almost always. You don't just build a thing. You build it incrementally, of course, but as you're building it incrementally, you just don't keep going. you get it so that it runs at these intermediate points. So you create a sequence of prototypes, a sequence of runnable prototypes that converge to your final solution. So this is our first prototype right there. So it prints 100 of these things, and it's a little hard to see 100. Let's start with 5, because it's easier to look at. Whoops. We'll start with 5 because it's easier for testing and development, and then we'll change it to 100 at the end. There's 5. Okay. But these aren't random, right? So now we got to make those random. And then I have a hint here. To solve the problem, you need to generate strings with 6 characters, where each character is randomly chosen from the following set of symbols. So we have a set of symbols there. We need to randomly select from that list. There's 16 of these symbols. These are the hexadecimal characters. Notice I'm not using the quotes, I'm using apostrophes to surround these. That's because these are single characters. We could use quotes as well, but it's more efficient just to use a single character notation. To make the choice random, you need to use the modulo operator, specifically use the expression rand16 to get a random integer between 0 and 15. So I'm not going to read the rest of it because I'm just going to explain it. And you can see we're going to need a random number generator. So let's include the ctime header. I think we also need, I'm not sure. Do we need C standard live upstairs? Maybe. And just to play it safe, put that in there. But maybe you don't need that. I don't need that, I know that. And then here we're going to seed the random number generator. We do this only once. Don't do this inside the loop. We looked at that already. We get the same sequence of random numbers. So srand, we're going to seed the random number generator. So the random number generator is a built-in facility that we can access when we need it. But we want to randomize it here. We're throwing in a seed values based on the number of seconds. So in some epoch. To scatter it a little bit so we get a different sequence each time we run the program. So maybe if I append, can I do that? I'm not sure I can do that. Can I do that? I can't remember this language. So can I append a numeric value onto a string? Is that legal? It is. That's convenient. Well, these are, I'm printing it as, it's converting this into a string. So we're looking at some strange characters there. So this isn't going to help us very much here. Okay. So let's do it like this. See, there's 2 loops here. We have to generate 6 random digits, and then hit a new line, and then generate another 6 random digits, and then another new line. You see that? There's a loop within a loop. So the inner loop is we're going to use another index j for that. So this is I less than 6. We want this inner loop to run exactly 6 times. All right, let's see. So I'll declare a color, set it to the empty string. Then inside here, I'll take color and I'll append a character. I'll call it E. So we're using single quotes here because that's a character. Let's append the color value. So we do it in here. So we're going to get 6 E's in a row. We're going to get 5 of them, and then we'll change it to 100 later. You see what I'm doing here? I'm trying to figure out what my next prototype is going to be. What's my next runnable instance of the program is going to look like. Oh, an infinite loop. What's going on? So, oh look, you see that? I never hit 6. You see that? That's an infinite loop there. It's locked up. Because I left an I there, I less than 6. Well, I gets to 5. You know, I mean, I is always less than 6. So we, in the very first pass of the loop, we just, the string is going to get infinitely large. It's going to have to crash. I mean, you know, I don't get it. Why isn't that crashing? Now let's kill it. So Control C. Killed the program. And I'll change that I to a J. I got that, get rid of that bug. You see the other benefit of doing the incremental development? If I kept coding without testing, that bug we'd have to get later on when the program was a lot bigger. There it is. Just to show you that again. There we go, 6 E's. But we don't want an E, we want a random value. So what we'll do here is we'll generate a random value K. So we call rand. Rand returns a random integer, but it's from 0 to some very big number. So we're gonna divide it by 16 and take the remainder. Now K is 0 to 15. That's 16 different states, 0 to 15. Right? 0 is 0, 1 is 1, 10 will be A, 11 will be B, and so on. Now there's at this point there's some clever ways to convert the value K into a hexadecimal value. There's some very clever ways to do it. I'm not going to show you the clever ways because I don't remember them, but we could look them up. I'm just going to show you the simple brute force way to do it. So if K is 0, then we're going to append, we're going to plus equals, that means append. We're going to append a 0. If K is a 1, we're going to append a 1. You see that? If K is a 2, we'll append a 2. Now I'm doing this in an inefficient way because it's better to have an else if there. So actually, they use a lookup table. If you're concerned about speed, if you have to do millions of these, we need to reorganize the code. But we're not solving that problem. We're just getting a basic solution here. That's not efficient because we're not expecting to do this a lot. So we're not going to do an efficient solution. We're going to be wasteful. We're going to be wasteful because we don't need an efficient solution. And being wasteful lets us make the code more readable. So, if you have a choice between readability and efficiency or speed, pick readability unless you really need the speed because you always need readability. If you're writing a video game and you're in some tight loop that runs a lot, then you're going to need to choose for speed and not readability at that point. But normally, most code can be written to be readable, and you can sacrifice some efficiency because it simply doesn't matter. So that's 3, 4, 5, 6, 7, 8, 9, 10, 15. Did I make any mistakes? Oops. 10, 11, 12, 13, 14, 15. Two, 3, 4, 5, 6, 7, 8, 9, A, and this is, whoops, replace with a B. That seems to work all right. That doesn't work well. All right, there we go. Just going to tighten everything up here. See how I'm doing the indents? All of this is inside the loop, so I have it indented to show that these statements are all in the for loop. Now this for loop runs 6 times. That's why we want this operation. Only one of these appends are going to run because k, k is only one of those values, so that only one of these tests will be true. And so we're going to append a hexadecimal digit, and then we'll do it 6 times. Oh, we're missing one thing. Oh no, here it is. Then we're gonna, then color has been set to 6, a string of 6 hexadecimal digits. We print it, then we print a new line, and then we increment I and do it all over again. And then we'll do it 100 times. We'll leave it at 5 for now. And you see, when we come back to restart the outer loop, we reset color back to an empty string. So this should do it right here. Oops. Look at that. Looks good. Those are random. Now we're going to fix this. Make that 100. That's 100. Well, I'm going to see it. I'll use this redirection operator. I'm going to, instead of send, I'm going to reassign a standard output stream to file t.txt. I'll just call it T. I don't need the TXT. See, it's not displaying on the console because I reassign a standard output stream from the console to the file T. That's just called a redirection operator. This is not part of C++ language. This is something that's available in the terminal window. So we can look at that. There's the file of 100 of these things. There's the 100 numbers right there. And I can set the line numbers. I can see that, yeah, there's 100. That's line 100 right there. All right. So that's it right there. So you do that one. So I gave you the solution actually to all of these, right? So we went through all of these. But in future labs, I want to warn you, I'm not going to do every single problem. But I know that these problems are difficult. I think detecting prime numbers was tough. Listing prime numbers was pretty tough. And you're just starting at this. So I'm just trying to get you going. But later, I'll provide less and less specific, solutions to the problems, although I'll discuss all the lab problems. Or I'll try to discuss all of them as needed. All right. So do we want to talk about the exam problems now? Is that all right? Okay. And what do you want to do? Which one of these? Yeah.
Number one on the additional practice problem,
This one right there?
the one all the way at the bottom,
The
the
additional.
additional practice.
Oh, the additional. Okay. I reset the numbering to 1. Oh, because I don't have solutions to those, do I?
Yes.
Yeah, this one here. Oh, what does this print to the console? You can check this one by coding it up and running it, right?
Yeah.
That's one way to do it. But so I'm going to assume you did that. And the reason you're asking me this is you want some hints about how to analyze this code. How do I approach it and analyze it and come up with a solution? All right, let's take a look at this one here. So this is the additional number 1. All right, let's look at this. This is going to, the problem is, what does this print? What does it print? Well, let's do a first observation is that this is the line where printing happens. And that line is inside the loop. So we're going to print something, potentially many times. So it's in this while loop, and that's the second loop of the program. So we start by declaring an I, initializing it to 1. So I've got this value I, and it's initially set to 1. And then here's a section. This is what it's going to output. This is what I'll put to, what it outputs there. So we basically have a loop here, while loop. So we're going to repeat the substatements. These are the substatements. We're going to repeat the substatements as long as the loop condition is true. This is the loop condition. When this condition evaluates to true, we'll execute the loop statements. And then we go back and evaluate the condition again. So the only way this is going to terminate is if we modify I, because the loop condition depends on I. So I starts at 1. 1 is less than 128. The loop condition is true. So we're going to print I plus 1. Well, I is 1. I plus 1 is 2. So we're going to print 2. What's I? It's 1. It's not 2. Remember that. I is not 2. This doesn't modify I. It uses I. Then we print the space. I already printed that. Then we go to the next line. This is where we modify I. We're assigning to I. So here's where I gets modified. And what gets assigned into I? When you write a compiler, you have to parse these lines and decide, what do you do first here? Because the compiler generates machine instructions to carry out, these commands in the higher level language. And it sees 2 operations. There's assignment there, and then there's multiplication. It says, oh, multiplication has higher precedence. I'm going to do that first. So the compiler generates code that does this operation first, and then the assignment into I. All right. Maybe. Because this is a very simple expression, so actually that might be doable all in one statement. I don't think enough about assembly language or machine instructions to quickly analyze that and know whether that's the case. So 2 times I is 2, and assign that into I, so I becomes 2. So when we're finished with this line, we've done all of the substatements. This is not a for loop. In a for loop, when you finish the substatements, you do the end of line operation. Like here, see that plus plus I? It only has one substatement down here. So when we finish this single substatement, then we're going to do the end of loop operation, which is to increment I. But in a while loop, there is no end of loop operation that's coded in there. This is the end of loop operation right there. So after we do the substatements and we reevaluate the loop condition, I is 2. We made a note of it over there. 2 is less than 128. So we're going to print 2 plus 1. So we're going to print 3, and then a space. And that's it. And I remains 2. And then we're going to compute 2 times I, so that becomes 4. And 4 is assigned into I, so now I becomes 4. And we finished the substatements, so we need to evaluate the loop condition. 4 is less than 128, so we do the loop again. So I plus 1 is 5, because I is 4. Going to print 5 in a space. And then we're going to double I. So I becomes 8. Now we're going to print 8 plus 1. Because now I got it, right? Now we can move. And then we double I, 16. And then we're going to print I plus 1. That's 17. I think we're on a roll here. So double that. It's 32. Print 32 plus 1. Now be careful when you're doing this. You make a mistake like I just did. And then I'm checking the loop condition. Oh, I's got to be less than 128. So double 64, that's still less than 128. Print 65. Double this. Double 64 is 128. Let's slow up here. The loop condition, is it true or false? False. So that means we've completed this statement. We don't do the substatements. We're done with that statement. We do the next statement, but there isn't any next statement. So we're finished. This is the output. That's not too bad, is it? But you're not going to get it if you don't practice. I can tell you that. You got to practice. This is an easy problem. And this is going to, if you're having trouble with the class, because some of you are overwhelmed and you're not interested actually, and practice this one and get a good grade on the first exam. And these kind of problems will come up on the final, and you'll get these problems on the final. And then the harder problems that are coming a little bit later, you've got some leeway there, So don't delay. Figure out how to do this kind of problem. All right, any others?
I have a question. Could you write that while loop as a for loop right there?
Yeah, actually, and that's the kind of problem I ask a lot. How do you write this while loop as a for loop? Let's do that. That is a typical problem. There's the code as a while loop. Now the for loop, so we have the initialization section, and then we have the condition, and then we have the end of loop operation, and then we do something in here. Well, this is the end of loop operation right there. I is 2 times I, right there. And then the statement that we run is this one. And the initialization is the declaration of I. Oops, that should be a 1. And the condition is I is less than 128. So that'll give you the same result. But you know, this line right here, you don't usually see that. See, this you don't normally see in a for loop. Usually you just see a simple increment at the end. This will give us the same result, I times equal 2. That's what you might see, because you expect something brief in the end of loop operation section in a for loop. So I wrote it as a while loop because that's what you would typically see it written as.
But if we were given a problem like that and we wrote the last part is I equals 2 times I.
Yeah, it's not a problem.
Okay.
Yeah. So any statement, you could put any statement in here that you like. Any other questions? You want to look at any other problems? Yeah. You want me to pick one random?
Can we see number 6?
6. Any additional section?
Yes.
All right. 6, when the code in figure 5 runs, that's this code here, what does it output to the console? Well, I is an integer value set to 1. J is an integer value set to 2. X is a floating point value set to 1.0. So we take an integer and divide by an integer. That's going to give us an integer. So what's 1 divided by 2 as an integer? 0. Is 0 bigger than 0? No. So it does not print alpha. So here we have a floating point number divided by an integer. That's going to give us a floating point number. So what's 1 divided by 2 as a floating point number? 0.5. Is that bigger than 0? Yes. So we're going to print beta. So just print beta. Oh, now, you got to know the, for the exam, you got to know these here. You have to know these. You need to know this, and you need to know this. And I'm going to ask questions like the following. Let me see, like, you know, like what does PWD do? Or you could say current working directory, like that. You could say this too. And you know, what does CD do?
Changes directory.
Yeah, changes. But I might ask another problem. Suppose you're in a folder and you want to make the parent folder your current folder. Show me the command to do that. How can you change your directory to the parent folder? Yeah? CD dot dot. That's how you go to the parent folder. Right? But suppose you're in a directory, you're in a folder, and your parent folder has a subfolder named temp. Okay? How do you change directory to that? That's good. You got it. That's how you move to a sibling folder. All right, how do you get rid of a directory? Suppose that temp is in your current directory. How do you get rid of it? RMDIR temp. The temp has to be what? Empty. Good. You know, this command only works when temp is empty. That's like a security precaution. You don't want to remove something that inadvertently. Suppose that temp is in your home directory. You know, you're somewhere in the file system. You want to remove the directory called temp that's in your home directory. What's the command for that?
RMDIR space tilde / temp.
That's it. Good. See, if I say operate on some folder in your home directory, use tilde to specify the home directory. That's this symbol down here. And dot is the current directory. So I'm going to ask you to, show the command to do something like this. And I'm also going to ask you to describe what something does. So those two kind of questions. So you need to know all of these. How do you copy? Suppose you have a file named ex1.cpp and you want to copy it to ex2.cpp. What's the command? That's great. You guys got it. That's the copy command. Suppose you wanted to copy a file named main in your current folder into the parent.
So
No, the parent.
the parent dot slash main dot cp.
Well, you could do this, but you don't need that. You could just do this.
Okay.
Actually, that'll work too.
Okay.
So, but
If you did the
if you
slash-
can't remember all those alternatives, this would do it. So remember, the copy command is copy, the source. This is how I write it. Copy the source to the destination. If the destination is a folder, it's copied into that folder. If the destination is a file name, it's copied, so on, like that. Okay, so those are those problems.
There's a question in the practice problems where it's something to the effect of what does the dot slash in front of the a dot out
Oh,
mean?
did I have that in there?
At the bottom.
Is it farther down? Oh, here. What does the dot in the following Unix command mean?
Just your current directory.
Current directory or current folder, you could say that. Good. That is the dot. All right. Is that enough? Okay. Good luck on Monday.